Welcome to the 21st lecture of the MOOC on parallel algorithms. In the previous lecture, we were proving a lower bound for sorting on the parallel comparison model. In particular, we had the expression CTN, which represents the number of comparisons that you must necessarily perform if you try to sort n elements in t steps on the parallel comparison model. So, we were seeking to prove a bound for Ct of n. In particular, we wanted to show that Ct of n is greater than or equal to t n power 1 plus 1 by t divided by e minus n t. We proved the basis, which involved showing that the claim holds for all ordered pairs of the form C1n and all ordered pairs of the form CT1. This we had done in the last lecture. Now, we were considering the expression Ct of n, where t and n are specific values of small t and small n. What we assumed is that, by the way of hypothesis, the statement held for all values of small n and small t that are less than capital N and capital T respectively. For example, we assume that for all n t such that n is less than or equal to capital N and t is less than capital T, or n is less than capital N and t is less than or equal to capital T, the claim held. And then we showed that Ct of n is governed by this recurrence relation. So, once we have this recurrence relation, we can use the induction hypothesis and substitute the claimed quantity for each of the C terms on the right hand side. Therefore, we can say that this is greater than or equal to and then substituting for the last term, we have t minus 1 into x power 1 plus 1 divided by t minus 1. So, that is the expression we get. If you gather some of the terms, we can simplify this as you would recall that e here is the base of the natural logarithm. But here these cancel out and we are left with n. So, if you take n inside the square bracket, we will have and when n goes into the square bracket, we have and of course minus nt. So, we know that Ct of n is greater than or equal to this. Now, this is almost in the desired form, except for the contents in the square bracket here. That is, we want to show that Ct of n is greater than or equal to t times n power 1 plus 1 by t by e minus nt. Instead, we have shown that it is t times n power 1 plus 1 by t minus e into this contents in the square bracket minus nt. So, if the contents in the square bracket turn out to be greater than or equal to 1, then we are done. So, let us focus on the contents in the square bracket and then show that that will be greater than or equal to 1. For this, we use the geometric arithmetic mean inequality. Which says that alpha a plus beta b is greater than or equal to a power alpha times b power beta, where alpha plus beta equal to 1 and alpha beta a b are all non-negative. So, let us use this and take alpha equals 1 minus 1 by t and beta equals 1 by t, and a as x power 1 plus 1 divided by t minus 1 divided by n power 1 plus 1 by t, and b as e by n power 1 by t. So, we are applying this to the second term and the third term within the square bracket. So, if you apply the geometric arithmetic mean inequality to the second and the third term, you find that these two terms together is greater than or equal to x power 1 plus 1 by t minus 1, which is t by t minus 1, this power, that is a power alpha, and then b is an e by n power 1 by t, that power beta, which is 1 by t. 1 minus 1 by t is t minus 1 by t. Therefore, in the exponent of x, the 2 will cancel out, that is t by t minus 1 and t minus 1 by t will cancel out, and we will be left with x. Therefore, this is nothing but x divided by n power 1 minus 1 by t squared, that is a power alpha, and b power alpha is this. So, simplifying, we get the sum of the second term and the third term put together will be at least x e power 1 by t divided by n. But then we know that the increasing sequence one plus 1 by t power t tends to e as t tends to infinity, which means the sequence converges to e from below. In particular, if you take a particular value of t, you have 1 plus 1 by capital T, power capital T is less than e, or in other words 1 plus 1 by t is less than e power 1 by t. This enables us to say that this is at most x times 1 plus 1 by t by n. In other words, the content within the square bracket is greater than or equal to 1 minus x by n to the power of 1 plus 1 by t, which is the first term, plus x by n into 1 plus 1 by t, which is the second term. Now, to the first term, let us apply Bernoulli's inequality. Which says that for any alpha less than or equal to 1 and for any t greater than or equal to 1, 1 minus alpha power t is greater than or equal to 1 minus alpha t. That establishes that the quantity within the square bracket is greater than or equal to one minus 1 plus 1 by t into x by n plus 1 plus 1 by t into x by n, which is equal to 1. So, that establishes that the contents within the square bracket is greater than or equal to 1, or Ct of n is greater than or equal to t into n power 1 plus 1 by t by e minus nt. So, that establishes the claim. Now, we say that from this claim we can derive a lower bound for sorting n items using p processor. Why is that? Let us say we have an algorithm that sorts n items using p processors. Then the cost of this algorithm is p into t, the processor time product. But then this parallel algorithm would have performed at most pt comparisons, which means at least Ct of n comparisons, which means pt is greater than or equal to Ct of n. The algorithm must necessarily perform Ct of n comparisons, and it has run in a total cost of pt. Therefore, pt has to be greater than or equal to Ct of n. In other words, if a sorting algorithm uses p processors and runs in t time, then the cost of the algorithm pt is greater than or equal to Ct of n, which is the smallest number of comparisons the algorithm has to perform if it has to run in t steps and yet sort n elements. So, pt is greater than or equal to Ct of n. But then we have already claimed that Ct of n is greater than or equal to t n power 1 plus 1 by t by e minus nt. So, that establishes that pt is greater than or equal to t n power 1 plus 1 by t by e minus nt. Dividing both sides by t, we have p greater than or equal to n plus 1 n power 1 plus 1 by t by e minus n, or in other words p by n plus 1 is greater than or equal to, that is dividing both sides by n and then moving the negative term to the other side, we have or n power 1 by t is less than or equal to e times p by n plus 1. If you take logarithm on both sides, you have 1 by t times log n less than or equal to t is greater than or equal to log n divided by log of e times p by n plus 1. That establishes that t is small omega of log n by log n by log of p by n plus 1, which is the same as saying that t is omega of log of n to the base p by n plus 1. So, this is a lower bound for sorting n items using p by n processes. So, let us try substituting some particular values for p. In particular, if p equal to n, p by n equals 1 and p by n plus 1 equal to 2, which means the lower bound is log n to the base 2. So, that establishes that when you have n processors, you will not be able to sort faster than log n time. So, in that sense, Cole's merge sort is an optimal algorithm. It sorts n elements using n processors in order log n time. You cannot expect to better Cole's merge sort in an asymptotic sense. If you put p equal to n by log n, n log n, then p by n is log n. Therefore, t would be omega log of n divided by double log of n. When you have n log n processors, you cannot expect to sort faster than log n by double log n on any of the P-RAM models. So, in particular, what we have shown is that Cole's merge sort is optimal. Now, let us begin a new topic. The new topic that we are going to see is the problem of finding connected components of a graph. So, we will assume an undirected, unweighted, undirected graph for now. And let us say the model that we are going to use is the CRCW arbitrary P-RAM. So, you must have all studied the connected components problem in the sequential setting, and you would have seen that this problem can be solved using DFS and BFS in the sequential setting. So, this is a reasonably easy problem to solve in the sequential setting. In particular, let me recall the problem for you. So, let us say we are given a graph G equal to VE. So, given this graph, what is necessary is to define a parent pointer for each vertex. For every vertex, we have to define a parent pointer, so that the vertex and its parent are in the same component, and we will have one star for every component. In other words, for the first component, let us say we can have a star of this sort. What this signifies is that 1, 2, 3 and 4 are all in the same component. So, we have identified this component with vertex 2, that is, in a sense we are identifying that vertices 1, 2, 3 and 4 all belong to the same component, and we are choosing to name this component as 2. So, 1, 3 and 4 all adopt 2 as their parents, and here let us say 5 points to 6, and therefore 6 is chosen to represent this component. And let us say the third component is chosen to be represented using the name of vertex 7. So, we are going to establish 3 components in the graph with names 2, 6 and 7 respectively. The other vertices in the component will end up pointing to the representative vertex. So, finding of connected components in the graph is essentially defining parent pointers in this sense. Every vertex ought to have a parent pointer. Every vertex belonging to the same component should have the same parent, and the parent of a component can point to itself. Therefore, every component essentially reduces to one single star graph. So, the goal is to find a star graph for every single component in the graph. So, the algorithm goes like this. Let us say we are given G in adjacency list representation. Which means we have an array of vertices, and for each vertex we have an adjacency list, which you can assume is doubly linked. So, such a representation is the adjacency list representation of the graph. So, let us assume that we have enough processors to occupy all the data values. We assume that we have one processor per vertex, and one processor per adjacency list entry. So, this is as good as assuming that you have n plus 2m processors, but since the model is self-simulating, we can simplify this into assuming that we have n plus m processors. So, when we say we have n plus m processors, that is as good as saying that we have one processor for every single data element of the graph. Now, the algorithm begins with an initialization, which we call step 0. In the 0th step, what we do is this: for every v, we define the parent pointer as pointing to itself. The parent is oneself for every vertex. So, this is the 0th step. And then in step 1, we have several iterations. So, step 1 is essentially a loop. Here we repeat the following steps. In step 1, for every edge uv, every directed edge uv, we assume that the graph consists of undirected edges, but then each undirected edge can be visualized as 2 directed edges, one in each direction, which means in the adjacency list we assume we have one entry corresponding to edge uv and another entry corresponding to edge vu, which are the twins of each other. So, for each adjacency list entry, That is, now I am visualizing the graph as a directed graph. So, for each directed edge UV belonging to E, we do in parallel. If U belongs to a star, in a moment I will show you how to check if U belongs to a star or not. If P of U less than P of V, P of U equal to P of V. So, that is what we do in step 1-1. And then in step 1-2, for every U belonging to V, we set P of U as P of P of P. This is one step of pointer jumping, exactly as we did in the case of list ranking. So, these are the two steps of the loop. We continue doing this until for every directed edge UV, P of U is the same as P of V. So, that is what the algorithm is. But we have to explain some things now. The parent pointers. The invariant of the algorithm is that every vertex has a parent pointer. Initially, for all V, we set that P of V equal to V. So, initially we have a set of vertices of this form. But we shall show that as we go along, we will have the parent pointers defining a tree. A collection of trees, a forest in particular. Each tree of the forest will be of this form. Every node in a tree will have an out degree of 1, and all nodes other than the root will be pointing to a node other than itself. The root will be pointing to itself. So, this establishes that every single node in the graph, in the graph defined by the parent pointers, the out degree of every single vertex is 1. Every vertex has got a unique parent. So, this we shall establish that the parent pointers will always define a forest in this sense. Our idea is that finally, when the algorithm ends, there should be one forest corresponding to every single component. What we define as a star graph is a tree of 2 levels. It has one root, and the root has several children, all of them pointing to the root itself. And then there are no grandchildren. The tree has only 2 levels. The root is at the first level and the children are at the second level. So, there are only 2 levels. A star graph is a tree of exactly 2 levels. So, what we want is that when the algorithm terminates, every tree in the forest must be a star graph, and there should be one tree corresponding to every single connected component in the forest. Now, the question comes, if you have one processor per vertex, detect if it belongs to a star graph. This is a condition that we have to check within the algorithm. Here we check whether U belongs to a star or not. So, we should be able to check whether a vertex U belongs to a star graph or not. But remember, we are doing this on an arbitrary CRCW param. This is done like this. Checking for the star property is done like this. Assuming that we have one vertex, one processor per vertex, let every vertex in the star graph discover its parent and the grandparent. So, for vertex V, we take the parent and the grandparent. If the parent and the grandparent are not the same vertex, then V is neither the root nor a child of the root. That is because the root points to itself. The parent of a root is itself. Now, consider a child of the root. So, let R be the root and let X be this vertex. Now, the parent of X is R and the grandparent of X is also R. So, for every child of R, the parent is R and the grandparent is also R. But here we are explicitly checking whether P of V is not the same as P of V. So, this condition is satisfied only if V is neither the root nor a child of the root, which means V does not belong to a star graph. So, for every vertex, if this condition is satisfied, V is not in a star graph. So, it is easy to check for all vertices that are neither roots nor children of roots. So, this can be established in order of one time. So, once this is done, every vertex other than the roots and children of roots know that they are not in star graphs. Now, the roots and the children of the roots have to find out for themselves. This can be done easily. If V is not in a star, then V has a grandparent which is not the same as V. Inform the grandparent of V that it is not in a star. Every V now informs every V that has found out that it is not in a star informs its grandparent that it is not in a star too. Now, if a tree has more than 2 levels, then the root certainly has grandchildren. Those grandchildren will now come and tell the root that it is not in a star. So, those roots which are of trees that are not stars now know that they are not roots of stars, and by omission all the other roots now know that they are roots of stars. For example, if a node has no grandchild and in this step it was expecting a grandchild to come and inform it that it is not in a star, but no grandchild comes. At that point, that vertex knows that it does not have a grandchild, which means it is a node of the star. So, all vertices, all roots of stars have now identified themselves correctly, and all roots of non-stars also have identified themselves correctly. And once the information is available with the parent, the children can immediately see. So, in the next step, every vertex V will go and check whether its parent belongs to a star or not. Now, if a vertex is a child of a root, it can check at the root now and discover that it belongs to a star or not. If V is a child of a root, check with the parent. So, we have a 3-step process to check whether a vertex belongs to star or not. Once these 3 steps are executed, we would have informed every single vertex as to whether it belongs to a star or not. The first step applies to every vertex checks that its parent and the grandparent are different. If these two are different, certainly V is not in a star graph. is not in a star graph. So every vertex that is a grandchild now has found out that it is in a star graph. The other vertices are still non-committal, they do not know. So if this condition doesn't satisfy, then the vertex still doesn't know. Then it goes on to the second step, and then if a vertex has found that it is not in a star graph, which means if it is a grandchild, so in the second step every grandchild is active. So every grandchild will go and inform its grandparent that you are not in a star graph too. So every grandparent has now found out that it is not in a star graph. In particular, every root which is a grandparent has found out that it is not in a star graph, and by omission every root that is in a star graph also has found out that it is in a star graph. Now all that remains is to inform the vertices which are children of the roots. So if a vertex is a child of a root, that is easy to check. Your parent and the grandparent are the same, then you are a child of a root, and your parent is different from yourself. In that case, you are a child of a root. Then all you have to do is to check with your parent. The parent already knows, the parent is a root, it already knows whether it is in a star or not. So you only have to copy the information from the parent. So in 3 steps, we have informed every single vertex of the graph as to whether it belongs to a star or not. Now we come to the description of the algorithm. In step 1, what we do is this: for every u which belongs to a star, we perform what is called hooking. Step 1 can be called the hooking step, and in step 2 we do one round of pointer jumping. This is called contracting. So the algorithm proceeds repeatedly hooking and contracting. So what exactly do we do here? In step 1 we execute if u belongs to a star. So u belongs to this star, let us say. U could be either the root or one of the children. Then see, we are doing this for every single edge of the graph. So consider some edge uv of the graph where u belongs to a star. So u may be one of these vertices, let us take this as u. And we are considering an edge in the graph. The dotted line represents a real edge in the graph, whereas a thick line represents a parent pointer. So this is an edge in the graph. So what we do is this: u belongs to a star, and that is why this edge gets to execute step 1. So in step 1, we check whether the parent of u, this is the parent of u, and this is the parent of v. We check if the parent of v has a number that is smaller than the number of parent of u. If that is the case, we make p of u. Right now p of u is pointing to itself. This we remove and then make p of v the parent of p of u. So this star ends up being a part of this tree. Why do we do this? At present in the algorithm we have 2 components defined by the parent pointers, that is u belongs to one component and v belongs to another component. Now u is in a star, which means this tree cannot be contracted any further using pointer jumping. So this component to which u belongs, this component in the graph defined by the parent pointers, u has come to a point of stagnation. This component cannot shrink any further. But then we find that there is an edge uv in the graph which connects this star graph, this 2-level tree, to another 2-level tree. Therefore, we attempt to hook these 2 trees together. That is because in the final reckoning, all these vertices should be in one single component and therefore in one single star graph. Therefore, what we are attempting to do here is legitimate. But then there could be several such attempts. We are doing this for every single edge uv. In step 1.1, we do this for every single edge uv. So when we consider these two trees, the tree to which u belongs and the tree to which v belongs, there could be multiple edges going between these two trees. Since the model that we are using is the CW arbitrary PRAM, when multiple processes attempt to hook these two trees together, exactly one of them will succeed. That is, multiple processes might be attempting to reset the value of P of u, but exactly one of them will succeed. For example, it could be that there is another vertex v prime which does the same thing. V prime attempts to hook P of u to P of v prime. That is because we have an edge u v prime 2 in the graph. So there is one process sitting on u v prime and another process sitting on u v. Both the processes recognize that P of u is less than P of v and P of v prime, therefore both the hookings are valid. Therefore, the first processor will attempt to reset P of u as P of v, whereas the second processor will attempt to reset P of u as P of v prime. Exactly one of these attempts will succeed on the arbitrary model. It does not really matter which one succeeds. Either way, we will be hooking this star to another tree. Now, there could be another edge going out of u into some other component, into some other tree, which will attempt to hook the star to that particular tree. So, once again, it does not really matter which of these attempts succeed, whichever succeeds will ensure that this star graph is hooked to one of the existing trees. So, this is a way of coalescing multiple trees into one single tree. And then after doing this, we will reduce the height of the trees by one step of pointer jumping. That is, every node will now adopt the grandparent of that node as its parent. When you apply pointer jumping to a star graph, nothing changes. The star graph continues to remain the same star graph. Therefore, you can perform a pointer jumping for every single vertex without concern about the star graphs ruining themselves. So, that is what the algorithm is. So, the correctness of the algorithm is easy to see. The correctness depends on the factor that no cycle is formed in the hooking step. This is because for all v, P of v is always less than v or less than or equal to v. Initially, P of v is the same as v, and whenever hooking happens in the first step, we will be hooking a vertex to a smaller vertex. For example, let us say you have an edge from u to v, a real edge in the graph. The process sitting on this edge looks at P of u and P of v. It finds that P of u is larger than P of v, and therefore it ends up hooking u to v. So, now this parent pointer that is defined is from a larger numbered vertex to a smaller numbered vertex, and this is true for every single pointer that is defined in the first step. Therefore, the parent pointer graph that we get after the first step is one where every vertex is pointing to a smaller numbered vertex. Then no cycle can be formed, and the pointer jumping will not violate this condition. Every node is adopting its grandparent as its parent. The parent is smaller than v and the grandparent is smaller than the parent. Therefore, the grandparent is smaller than the vertex itself. Therefore, pointer jumping will not violate this condition. So, this condition is satisfied at the end of the first iteration, and then it will be satisfied in the further iterations. For example, in step 1.1, what we do is this: we set P of v, P of u as P of v for all uv such that U is in a star graph and P of U is greater than P of V. Now, the new pointer being defined here is this. The pointer is from P of U to P of V. So, we explicitly check that P of U is greater than P of V. Therefore, the new pointer that is being defined is from a larger node to a smaller node. Therefore, this condition is maintained by every single pointer that is defined in step 1.1. Whenever you change the parent, you ensure that the new parent is smaller than the vertex itself. So, this invariant is always maintained. Therefore, the P graph, the graph defined by the P pointers, is always a forest. Therefore, pointer jumping defined on this is a valid operation. It reduces the height of the tree. And when the tree becomes a star graph finally, it will hook once again. So, the correctness of the algorithm follows from this. That is, if you keep doing this, eventually all the fragmented trees that we had from one single component at the end of the first iteration will end up hooking to each other, and eventually all of them will contract into one single star graph. So, if you imagine how the one single component operates, you will get to see that the algorithm operates correctly. Initially, every vertex is pointing to itself, then at the end of the first step, the vertices are hooking up somehow, but every hookup is guided by one single edge. Therefore, every vertex is hooking to some of its neighbors. But then, if you look at one particular component, you find that it might have several trees within this component. Then, these trees coalesce as steps go by. Whenever a tree shrinks to a star graph, it will hook again, but the hooking again will be directed by one real edge of the graph. Therefore, it will be hooking to another tree belonging to the same component. So, trees are now coalescing in this fashion, and then once the trees coalesce, we allow them to shortcut. So, we will continue this operation until every vertex has belonged to a star graph. Now, we have to estimate the running time. The running time can be estimated by looking at the total height of all the trees put together. Initially, when the vertices hook to form a collection of trees, the total height is less than or equal to n minus 1. This is because the worst that can happen is trees hooking up in this fashion. If the nodes hook up in this fashion, we have a tree of a single tree of height n minus 1. Therefore, the total height of all the trees put together is n minus 1 itself. The degenerate cases where the nodes pair off in this fashion. In this case, the total height of all the trees put together is n by 2. So, either way, we can see that the total height of all the trees put together is even more degenerate as a single star graph. It could be that all vertices belong to the same component and one single star graph is formed in one go in the beginning. Therefore, we can say that the total weight of all the trees put together that are formed in the beginning is n minus 1. And then we claim that in each iteration, the total height reduces by 3 by 2, by at least 3 by 2, by a fraction which is at least 3 by 2. Why is this? First consider the hooking step. In the hooking step we have a star graph of height 1 hooking to a tree of, let us say, height h. The total height of these two trees put together is h plus 1 in the beginning, before the hooking. Now let us say we are considering some u here, the u could be either the root or a leaf here, and we consider a v which happens to be a leaf of this tree. Therefore, the hooking happens this way. The parent of u is hooking to the parent of v. So, this tree, the tree of height 1, ends up hanging as a child of the parent of v. So, this is how the tree is going to be hung. Therefore, the total height of the new tree is going to be h plus 1. Now, this tree has vanished. It has become a part of the bigger tree which has a height of h plus 1. Therefore, hooking preserves the total height in this case. But in case the tree is hooking to some other node inside, further inside this bigger tree, then the height of the bigger tree will not increase because of this hooking. And it could be that several stars are hooking to this one tree. Therefore, we can say that hooking will not increase the total height of all the trees put together. It might decrease the total weight of all the trees put together, but it can never increase the total weight of all the trees put together. Therefore, the total height in the worst case remains the same when we hook. When we come to the contract step, this is a pointer jumping case. So, let us consider the individual trees. Of course, since we are considering pointer jumping, we might as well consider linked lists. So, in this case, when you have a linked list of 5 nodes, for example, there are 5 nodes, therefore, the height is 4. When we perform pointer jumping, one is pointing to itself, which is the root. So, 1 will continue to point to itself, 2 will continue to point to 1, 4 will point to 2. Now, 4 has a depth of 2, 3 will point to 1, and 5 will point to 3. So, you find that the height has now reduced to 2. So, if you take the ratio of the old height to the new height, you find that it is 2, which means in the contract step, whenever we are considering a tree of even height, the height reduces by a factor of 2. For all trees of even height, the height reduces by a factor of 2. If you consider a tree of odd height, where one points to itself, you find that the pointers flow like this. 6 becomes a child of 4, 4 becomes a child of 2, 5 becomes a child of 3, which becomes a child of 1. So, here we had a height of 5, whereas here we have a height of 3. The new height is 3. So, the old height divided by the new height in this case is 5 by 3. In general, if you take a tree of height 2n minus 1, the new height is going to be n, or in other words, the ratio is going to be 2n minus 1 divided by n. This is maximized when n equal to 2. When n equal to 2, the ratio becomes 3/2. Or this is the minimum. The ratio, the least ratio is 3/2. For any other value of n, we have a better ratio. So therefore, the worst that can happen is that the total height reduces by a factor of 3/2 in every iteration. The total height that we are beginning with was less than or equal to n minus 1. And finally, we will have a height of 1 for every single star graph. That is, we will have 1 star for each component. Therefore, the total height for each component is going to be at most 1. So this establishes that the total time required to reduce the height to a constant or to the least possible is log n to the base 3/2, which is order of log n. So what we have established is that connected components can be found in order of log n time using n plus m processors, where m is the number of edges and n is the number of vertices on a CRCW arbitrary PRAM. In the next lecture, we will try to solve the same problem on an ER EW PRAM. So that is it from this lecture. Hope to see you in the next lecture. Thank you.